Good afternoon, everyone. Our first speaker is Professor Simon Phillips from University of Chicago. He will talk about measure and topological rigidity beyond homogeneous dynamics. Let's welcome.
Thank you so much for the introduction, and thanks to the organizers for the opportunity to be part of this event. I've been learning a lot, and I hope I'll continue to do so. So today I want to speak about some joint work with most of the work will be joint work with Aaron Brown, Alex Eskin, and Federico Rodriguez Hertz. But in the beginning, I'll also mention a theorem that's joined with Ben Lowe and David Fisher. And our ultimate goal, is to try to obtain certain measure and topological rigidity results in dynamical systems, and for quite general dynamical systems. And I'll try to explain what that means, so what kind of results one tries to obtain. But I want to begin with a theorem that is quite elementary to state, and works as kind of as a motivation for what I'll be talking next, which will take some time to develop. So this is, as I mentioned, this joint result with David Fisher and Ben Lowe. And the theorem is the following. So the starting point is a manifold. We assume that it's negatively curved. It can have, in fact, the theorem is most interesting when it has variable curvature, but it has to be negative. So it's a Riemannian manifold. And another important assumption is that it's analytic. So we want an analytic Riemannian metric. And, but otherwise, no further assumptions. And it's closed, so compact without boundary. And the dimension is at least 3. And the assumption is that, so we suppose that M contains infinitely many totally geodesic hypersurfaces. So if M is 3 or more, hypersurfaces are genuine things. In general, if you're a surface, you have many closed geodesics. So on a surface, this theorem is not interesting. But if you are in dimension 3 or higher, and you have infinitely many totally geodesic hypersurfaces, then that turns out to be extremely exceptional. So in fact, very few manifolds have it. And this assumption alone implies that your manifold is not just, so first of all, it has to be what's called a hyperbolic manifold, meaning that this curvature, negative curvature, is everywhere constant. Everywhere the sectional curvature is the same. So it's the universal covers hyperbolic n space. And furthermore, it's what's called an arithmetic hyperbolic manifold. So arithmetic means that this group gamma comes from some arithmetic construction coming from number theory. So in general, there's lots of discrete subgroups of isometries of hyperbolic n space that lead to closed manifolds. But there's a very special class among them, which are these arithmetic ones. And there's an equivalent way to state this theorem, which is maybe a little bit more interesting because it says something about every manifold that's negatively curved, which is the conclusion, to say it contrapositively, is that M can have only finitely many totally geodesic hypersurfaces, unless it's extremely exceptional, extremely symmetric, so it has to be hyperbolic and arithmetic. So in this form, this theorem applies to all negatively curved manifolds. So it says they have only finitely many such totally geodesic hypersurfaces. So maybe a few comments about this theorem. The first one is that, in fact, what we show is that the manifold M has to be, if it has infinitely many totally geodesic hypersurfaces, it has to be homogeneous. So we only show that it has negative constant sectional curvature. And once you assume that, there's a separate theorem, which was proved recently, but a few years ago, by 2 groups of people, by Bader, Fisher, Miller, and Stover, for all n, and for n equals 3 by Margulis and Mohammadi. And they proved that if you so they begin with a homogeneous manifold, and they assume that if you have infinitely many totally geodesic hypersurfaces, then you have to be an arithmetic object. And so this was a conjecture of Reed and McMullen. The other remark about this theorem is that this theorem is sharp in the sense that it fails on the n sphere. So what I mean by that is that there exist analytic metrics on Sn which are not the homogeneous round metric, but for which there are infinitely many hypersurfaces, codimension 1 spheres for which are totally geodesic. So this fails in positive curvature. It also fails locally in the sense that you can construct negatively curved Riemannian metrics, in fact, complete such Riemannian metrics that don't live on closed manifolds and on which you have infinitely many totally geodesic things. And maybe the other comment is that in the arithmetic case, you definitely have infinitely many such hypersurfaces, where you might have none. So there's this kind of dichotomy, which, and then what's responsible for this is the fact that these arithmetic manifolds have extra symmetries that are not visible directly, and they're called Hecke operators. So if you have at least one such totally geodesic hypersurface, then you can have infinitely many. So you can keep generating them. And it might be that you have none. Yeah?
So when you say totally geodesic hypersurface, you mean
Immersed. Immersed. So they can have self-intersections. Maybe I should have used this word, but immersed. So they can have self-intersections, and you certainly allow self-intersections.
But they have to set that control.
Which set? So that's a good question. So you can assume that either you can have a different statement, which is that if you have even one immersed submanifold which is not closed, which doesn't close up, then you would expect the same conclusion. This is the first half, like the homogeneity, and I think that we can prove that it's funny, but in odd dimensions, but not in even dimensions, not in all even dimensions.
Maybe my question is more, so if I'm at any point in this map, I say any two layers of that form, can't I always extend it to the
No. If you, in general, if you have a Riemannian metric, which is not homogeneous, so no, the whole point is that M is not assumed homogeneous. So in general, if you have a inhomogeneous Riemannian metric, you might not have locally any totally geodesic hypersurface. Any other question? Yeah. Yeah, so in fact, maybe let me say this. So our theorem is a little bit more general. We can assume finite volume plus some extra conditions, some technical conditions that ensure that things are well behaved. In fact, what we need is that M has not negative curvature, but what's called Anosov geodesic flow. So as soon as the geodesic flow is Anosov, and in fact, this is a theorem really about the geodesic flow. So in order to prove this result, you have to study the geodesic flow on this manifold M, and the property that we really need is Anosov. So you can have a little bit of positive curvature, but as long as it's not too much, this theorem still holds. Okay, so one thing that is quite natural to expect in this situation is, and based on analogies with other theorems that exist also in kind of more number theoretic or arithmetic situations, is that you would like to have a similar kind of theorem for any k-dimensional totally geodesic submanifold. So instead of saying hypersurface, you could allow any k-dimensional submanifold that's totally geodesic, except that k should be at least 2, and you can go up to the codimension 1. But then the conclusion would be more complicated. You would like to say that if you have infinitely many k-dimensional totally geodesic submanifolds, then they have to be accounted for by having inside of your manifold, some further submanifold, which is one of these arithmetic homogeneous manifolds. So you could imagine the situation where you have one arithmetic homogeneous manifold, it lives inside a bigger manifold, and then all the two-dimensional, let's say, totally geodesic submanifolds are stuck inside this intermediate object. So you can have this kind of more complicated structure, and we expect that such a theorem is true, and it would be more complicated to prove. In fact, one also has to account for the fact that there's, besides real hyperbolic space, there's also complex hyperbolic space, there's quaternionic hyperbolic space, and a few other exceptional homogeneous spaces that one has to worry about as possibilities for these kinds of intermediate subspaces, submanifolds. So what I want to talk in the rest of the time is some tools that we hope can be used to attack the intermediate problem. So when you have these submanifolds that are totally geodesic, but they're not hypersurfaces. So I should say that the proof of this theorem on the previous slide is, I would say, in some ways by some kind of ad hoc methods. So it doesn't use any kind of general theory. We just kind of prove it by hand. But what I want to talk about next is some kind of general theory that allows to prove, we hope eventually will allow us to prove more theorems that are of this style. So you make some very weak assumptions about your underlying dynamical system, so in this case, the geodesic flow and submanifold, and you can try to get some very strong conclusions about what kind of dynamical system can admit such objects. So maybe one remark is that the way I'm presenting here things is a little bit out of sequence of how things developed. So this theorem on the previous slide, we proved it quite recently, whereas the project I'm going to talk about now has been going on for a long time. So it's kind of, I'm using kind of things a little bit out of order to motivate the results. So first I'm going to talk about smooth dynamical systems and this notion of hyperbolicity. So this is kind of a basic concept in dynamical systems, so I'll try to explain what that is about. And then I'm going to talk about a tool that is crucial for a lot of what we do. It's called the theory of normal forms. So I'll explain what that is. It's a tool, again, that arises in dynamical systems. And then I'm going to tell you about the main theorem. And our main theorem is quite general. It applies to essentially any flow with some assumptions that I'll state, and I'll try to explain what these assumptions mean. And it gives you some kind of useful conclusions about quite general dynamical systems. And then from this main theorem, I'll try to explain some more concrete consequences that are maybe easier to state than the main theorem itself. And then I'll try to outline a little bit what we want to do more with this main theorem. Okay. So, so hyperbolicity. So, as I said, we're going to study a dynamical system. So, what does that mean? So, in general, in dynamics, you can study quite arbitrary measure spaces, but we're going to restrict to a manifold Q. And we're going to have a flow on the manifold, meaning that it's a transformation that depends on time. And if you compose these two things, then the time adds up. I'm discussing everything here in continuous time, but that is not so important. So it can be discrete time as well. That's not, it's just a kind of a cosmetic thing. And we assume that mu is an invariant probability measure, and it's ergodic, which means that you can't break up your space into two sets of non-trivial measure, and each of those sets is invariant by the flow. So it's some kind of irreducibility assumption, this ergodicity. And the basic theorem in this setting is this theorem of Osseledets. And what does it tell you? It tells you that, so maybe I should say, what kind of theorem is this Osseledets theorem? It's an ergodic theorem, which tells you that if you run things for a long time, then you start seeing some kind of limiting behavior. And what the theorem, so the Birkhoff ergodic theorem, your observable is usually some function on your space. In the Osseledets theorem, the observable is the derivative of the transformation, the derivative of the flow, GT. So the conclusion is that you have a decomposition of your tangent bundle of your manifold into three spaces, three subbundles. And it's a measurable decomposition, so it's with respect to this mu measure. And there's a stable subspace, the unstable subspace, and the central subspace. And in the stable subspace, you have a further decomposition. So there are these numbers, lambda 1 through lambda n, which are called Lyapunov exponents. And so the theorem tells you that such numbers exist. And you have a decomposition of the stable subspace into these subbundles. And what is the characterization of these subbundles? It says if you start with any vector v in one of these w with sign negative lambda I, the negative lambda I tells you that it grows as t goes to plus infinity. The growth rate of this vector is roughly e to the minus lambda I times t. So stable means that this vector, as you flow it into the future, tangentially it gets contracted and gets contracted exponentially fast. Correspondingly, the unstable subspace, it means that you get here positive numbers. So in the unstable direction, things get expanded exponentially fast. And in the central direction, things might grow or might decay, but they do not. So if you look at them at an exponential time scale, they are roughly, so these exponents are 0. So they do not grow or decay exponentially. It means the following, that these subspaces exist on a set of full mu measure, and the way they depend on the point is also measurable. So they usually don't have very good regularity properties. Although that can be also fixed. In fact, they're a little bit regular, but they're a little bit better than measurable, but still not quite very friendly. They're not like usual smooth bundles. Okay, so as I said, these lambdas are called Lyapunov exponents, and the center direction has only 0 Lyapunov exponents. And maybe I should comment that this Oscillatus theorem does not tell you that these numbers are non-zero. So usually you need to assume or verify by some other means that you have a non-trivial such decomposition. So in fact, there are dynamical systems where this decomposition is completely trivial. There's only the center subspace and no vector grows exponentially fast or slow. So here I put a strict inequality, but I didn't say that this is a one-dimensional subspace. So this subspace could have a positive dimension, more than one. Okay. So the next thing that you want to do is, after you understand the tangential dynamics on the manifold, is you want to understand kind of things to higher order. And one way to do so is using this notion of stable manifolds. So what it means is, so if you go back to this decomposition at the tangent level, the stable manifold theorem, which goes back to Adamar and Perron, says the following, that if you look, so lambda n, if you remember, it was the smallest, the number closest to 0. So if you fix kappa that's even smaller than all the lambda i's, but still positive, at almost every point in your manifold, you have an immersed submanifold called the stable manifold. And the characterization of points on the stable manifold is the following, that Q prime is in the stable manifold of Q, if and only if, when you flow into the future, these points, Q and Q prime, get attracted to each other exponentially fast. So this is the characterization of the stable manifold. You have an analogous unstable manifold. So maybe I should add, there's this, in dynamics, whenever you have some theorem that tells you what happens in positive time, by reversing time, you have another theorem that tells you what happens in negative time. And in this case, you'll have an unstable manifold, which says that points on the unstable manifold get contracted if you flow into the past. And the problem is, of course, that if you take 2 points on the unstable manifold and flow into the future, they separate exponentially fast. And once they've separated, you can't say anything useful. They're usually as regular, maybe one less regular than the map, than the dynamics GT. So if the GT is smooth, then these are smooth. So you lose about one derivative or 1 plus epsilon, depending on how you prove things. Oh, yeah, sorry. So I didn't say what's the relation between the curly WS and the plain WS. And the statement that I didn't include is that this curly WS contains Q, of course, and its tangent space at Q is this space. So in that case, so they have the same dimension and they match. So it's a kind of nonlinear extension of the tangent space. The kappa is, it's true for arbitrary kappa. So there's another maybe technical point here. So you see that I said less than or equal to with this tilde, where the tilde means that the thing depends on the subscript here. So there's a constant in front, and the constant might depend on the points, and technically also kappa. But so you can take kappa. The theorem gets better as kappa approaches lambda n. So you get faster contraction, but you cannot quite take lambda n for your kappa. But other than that, you can get arbitrarily close. Well, so it's certainly invariant because of this characterization. Because if this is true at one time, so if I flow 2 points, then this will be true. You know, if I flow for 3 seconds, both points, then still be stably related. Yeah. So. There's a related theorem, which, to be honest, I'm not sure who to attribute to, but it's called the center stable manifold theorem. And you can ask what happens in the center direction. So now you take the direct sum of the center subspace and the stable subspace. But in this case, you no longer have an actual manifold. What you have is a germ of a manifold, which just means a Taylor series, a formal Taylor series. And so if you choose a realization of that Taylor series, so you probably know this theorem. If you have some Taylor series, there exists a smooth function with that Taylor series. So if there exists a germ of a manifold, then in fact, like a Taylor formal manifold, there exists a smooth manifold which kind of realizes it. So this center stable manifold is no longer canonical, unlike the object here, the stable manifold. And the property is that Q prime is in the center stable manifold of Q, if and only if, so you fix epsilon bigger than 0, 2 points, they do not diverge too fast. So for any epsilon, they diverge worst, like e to the epsilon t. So they're allowed to diverge, but they should diverge very slowly. And you allow yourself your epsilon to be strictly positive and arbitrarily small. And maybe to come back to the earlier question, unlike the stable manifold, so this condition is invariant by the flow, this condition is no longer invariant. So if you, yeah, so if you flow, then so you have to choose a center stable manifold, the realization, and then if you flow it, then at the next point they then need to be connected by the same condition. Okay, so these are kind of general results from dynamics. Now, I want to kind of specialize to the case of homogeneous dynamics to kind of apologize. So, in the case of homogeneous spaces of Lie groups, these theorems are much simpler, and you don't have to kind of invoke these more complicated structures. So if your manifold Q is of the form G mod gamma, where G is some Lie group and gamma is a lattice in that Lie group, and your flow is given by basically a one-parameter subgroup of your Lie group. So let's say you fix it to be a semi-simple element of the Lie algebra, and A is a Cartan subalgebra, where if you think of G as SLN, you can think of A as diagonal matrices in the Lie algebra. And in this case, well, what are the stable manifolds? In this case, you have, so if you fix your X in your Lie algebra, then the entire Lie algebra splits into 3 pieces. If you look at the adjoint action of X on the Lie algebra of G, there's things with eigenvalue less than 0 and greater than 0, or maybe I want to say, you have to look at the real part. So because I'm looking at the Lie algebra, the real part is either less than 0, greater than 0, or the real part is 0. So if you have imaginary eigenvalues, the one-parameter subgroup is rotation in that subspace. And in this case, the stable manifold is the exponential of, is given by a Lie subgroup of your Lie group G, and it's a nilpotent Lie group with a nilpotent Lie algebra n minus. So the adjoint action of X on this n minus is contracting. And so you have this Lie group structure, but more importantly, you have not just a center stable manifold, but you have an honest center manifold where you can exponentiate the direction in your Lie group that commutes with this one-parameter subgroup. And so you have a kind of a very rigid group theoretic structure. And in this case, there's a lot of theorems that tell you that you can have very few measures or closed sets which are invariant by such structures. So if you're looking at measures or closed sets that are invariant by nilpotent or unipotent Lie groups, so this is basically the subject. So the most general theorems were proved by Ratner. I think maybe the first theorems in this direction were due to Hedlund, and many people contributed to understanding and showing that if you have a measure which is invariant by this unipotent subgroup, in fact, any unipotent subgroup, n prime, that's non-trivial, then it has to be a very friendly measure. It has to be, there has to be a submanifold that contains that measure, and your measure has to be Lebesgue measure on that manifold. So in general, if you have a general dynamical system, your invariant measures can be extremely complicated and you cannot describe them. For these unipotent groups, invariant measures have to be rigid. They belong to a small list of possibilities, and you can determine usually which one it is. There's a related situation where you consider measures invariant by abelian subgroups, so any commuting set of flows, and you have to consider more than just one flow. So this is called higher rank abelian rigidity or dynamics. So you have two commuting flows, two or more commuting flows, and then turns out again you can classify the invariant measures under some assumptions, and again they have to satisfy a number of rigidity properties. So this is all kind of a large body of work in homogeneous dynamics, and what I want to talk about is some kind of extensions of some of these results in this in the smooth setting. So for general smooth dynamical systems. And maybe the first question to address is what, so in the homogeneous case, you had your stable manifold was in fact a Lie group. So you had a very nice structure in the manifold. It was in fact a Lie group. So what I want to explain is what you can do to replace that homogeneous structure and put it on the stable manifold for a general dynamical system. And the answer is this theory of normal forms. And one thing that comes in when you look at these normal forms is that unlike in homogeneous dynamics where everything is essentially controlled by the tangent bundle. So if you know the Lie algebra, you know the Lie group, and so somehow everything is controlled by just finite dimensional matrices. Once you look at general non-homogeneous smooth dynamical systems, you have to take into account these higher order jets that can arise in your dynamical system. And one way to address this is using this theory of normal forms, which I think was started with Poincaré, who basically, the theory of normal forms asks the following kind of question. If you have, let's say, a transformation, let's say a general smooth map, how can you conjugate it to make it look simpler, to belong to some standard class of maps that you can analyze then? And maybe the most famous normal form is Jordan normal form. So if you have any matrix, you can always bring it to Jordan normal form. Poincaré asked similar kinds of questions. If you have a transformation, let's say that a smooth map of Rn or C to the n that preserves the origin, and let's say smooth or analytic, then by smooth or analytic change of coordinates, can you bring it to some more friendly form? And there's various theorems of this type. And many people have contributed and continue to contribute to it. So the version that we need essentially comes from the work of Kalinin and Sadovskaya. What we had to do is we had to take a little bit the results that people proved in that situation and kind of reinterpret a little bit the statements and in terms of some kind of geometric structure. So the theorem that comes out of this whole story is the following, that suppose you have these Lyapunov exponents on your stable subspace, then associated to just these numbers, there's this notion of subresonant structure. So I'll explain what this means, but the conclusion, the statement is that the stable manifold admits a subresonant structure with parameters given by these Lyapunov exponents. So I'll explain in a moment what this subresonant structure is, but in an example, but the structure means the following. You have this manifold, basically, that you can think of as Rn, the stable manifold, and it has a group of automorphisms, a finite dimensional Lie group of subresonant maps that preserve this subresonant structure. And to have a subresonant structure means that your manifold is glued out of charts where the transition maps are elements of this finite dimensional Lie group of subresonant maps. And these subresonant maps they are basically, they sit in an exact sequence, or you can think of it as a semi-direct product. You can split this if you want, where there's the resonant maps and there are the strictly subresonant maps. And these strictly subresonant maps are the unipotent transformations. And the resonant maps, they are some kind of extension of these diagonal transformations. So, and the key feature for us is that you have this unipotent group which acts on your stable manifold and acts, in fact, transitively. And this endows it with some kind of structure that you can start analyzing. So also important is that, of course, this subresonant structure is preserved by the dynamics. So the transformations from one stable manifold to the next, they can be, in general, they're arbitrary smooth maps, but if you change your coordinate system to be in this subresonant form, then your transformations belong to some finite dimensional Lie group in the appropriate coordinate system. Sorry? Yeah, so I'll explain in an example. So I want to do an example now because it's a little bit technical, so it's a little bit easier to just give an example. No, it's a group of polynomial maps. So here's an example. So suppose that your derivative dynamics has two Lyapunov exponents, lambda 1 and lambda 2, and I'm assuming lambda 2 is bigger than lambda 1. So it's a two-dimensional manifold, the stable manifold, but the group of subresonant maps is all maps of the following form. You have x, y goes to, so in the linear part, you just scale things, but in the x direction, the one that's scaled by lambda 2, you allow any power, you can shear by adding any power of y as long as k times lambda 1 is less than lambda 2. So you can check that these maps that I wrote here, if you compose two such maps, then you get another map of this type. So they actually form a group. So so you allow translations, that's kind of trivial, but you allow also these shears, these polynomial shears, that only affect the x coordinate by y. So if you compose two such things, you're going to get something of the same form. And the strictly subresonant maps, they are the ones for which you do not allow any scaling. You allow only shears. So you allow translations, but you allow these polynomial shears as well. So maybe one thing to remark is that, so this is a unipotent group. In fact, in this case, it's pretty much an abelian group, but you can get more interesting unipotent groups once you go to higher dimension. And one thing to remark is that even though it's a two-dimensional manifold, the dimension of the group is not, it could be arbitrary. So it really depends on just these two numbers, lambda 1 and lambda 2. Okay. And as you can guess, resonant means that you can also have, if you have this k times lambda 1 equals lambda 2 for some integer k, then that refers to a resonant situation. Okay.
So this you said that is almost like the actual splitting itself, is there any other drive?
So it's at least measurable. You can say something a little bit more, which is that if you allow yourself to, so you know that any measurable function, if you discard a set of small measure, it's continuous. In this case, if you allow yourself to discard a set of small measure, it's going to be actually Holder continuous. So it's a little bit better than continuous, a little bit better than measurable, but definitely doesn't vary in a smooth way. Yes. So you can say it's polynomial maps which have a certain property that if you conjugate by these kinds of diagonal maps, then certain limits exist. So there's a different way to describe it that makes it a little bit more apparent. Any other questions? Okay, so to state the main theorem, I have to explain this notion of Gibbs states and what are generalized Gibbs states. So again, we're in the setting of a smooth manifold with a flow and an invariant measure. And one way to study the invariant measure mu is to disintegrate it. So, okay, try to draw a picture. So if this is your manifold Q, then you have this foliation by the stable manifolds. And your measure mu, it's some kind of cloud here, and there's this concept of leafwise or conditional measure where you cannot really restrict the measure to a submanifold, but there's a certain technique in measure theory and in dynamical systems that allows you to obtain a measure on almost every submanifold, almost every stable manifold, and such that the full measure is some kind of average of these conditional measures. So it's a certain technique for studying your measure kind of one slice at a time. So you can construct these conditional measures. And there's a classical notion, so people say that, I think it goes back to Sinai, that mu is a Gibbs state if, when you look at these conditional measures, mu u, so one thing I should have said, you notice I switched to unstables, from stables to unstables. It's just a cosmetic thing, but you can always reverse time. So mu is a Gibbs state if these conditional measures are of Lebesgue class. So when you disintegrate mu, it looks like Lebesgue measure on these submanifolds. It doesn't mean that mu itself is Lebesgue measure, because the way this foliation looks like could be quite complicated, but at least on the stable or unstable manifolds, it's of Lebesgue class. So this is for almost every Q. So everything here happens at almost every Q. There's also a notion of generalized Gibbs state. There's a notion of U Gibbs state, which I will not define. But what we need for our theorem is the notion of generalized U Gibbs state, which means something like this. Instead of being Lebesgue on the full manifold Q, or on the full stable manifold, you allow yourself to have a family of subgroups of these strictly subresonant maps. So remember, this is a unipotent group. So this U plus itself is a unipotent Lie group. And what you're asking is for this measure, the conditional measure, to be invariant not under the full group GSSR, but rather under a subgroup U plus. Yeah. Yeah. So these stable manifolds are immersed. So these stable manifolds, they're immersed, right? And they admit a map from Rn onto the manifold. So once you have a small piece, you can expand it by growing it. And once you've grown it as an abstract manifold, you get an action on this whole group, on the whole manifold. So, I mean, it's like when you have even a Lie group, when you have the unipotent direction, I mean, you have this immersed submanifold, and you have a Lie group action there. Of course, you're typically not interested in acting by huge elements. You do everything locally, but once you have a local statement, you can always grow it. So these generalized U-Gibbs states, what they mean is that when you look at these conditional measures, they are homogeneous, but only in certain directions. And the directions in which you're asking to be homogeneous are given by some family of unipotent subgroups, U plus. No, so certainly, I mean, even in the example I gave, the strictly subresonant maps were of arbitrary dimension, even though your stable manifold was two-dimensional. So, but if, I will say, the invariant measures and unipotent groups acting on Rn, like in this kind of polynomial way, they're not too badly behaved. You don't have any kind of issues with the fact that the action is not free. So there's also some extra technical conditions for what the generalized U-Gibbs state is, but as a general idea, this is what you should think of, is that you have these conditional measures on the stable manifolds, and they have to be homogeneous, but only in certain directions. Okay, so finally I can state the main theorem. So the setting is as before, and now suppose that you have one of these generalized U-Gibbs states. And this group U plus, so what I mean is that this group U plus is non-trivial. So you need to start somewhere. And this theorem is like a step of the induction. So the base is that you have some kind of invariance. And the conclusion is that if this family satisfies a condition called Q and I. So I'll explain what Q and I means, and we certainly need some assumption, and I'll explain what the meaning of this assumption is. Then if you have this thing satisfied, then you can make your group larger. So it means that your measure, you thought it was invariant under this group U plus, but it turns out that it's actually invariant under a larger subgroup. So it's kind of an extra invariant statement, which if you're familiar with how many of these rigidity results are proved in homogeneous dynamics, you always have this extra invariance step. So you want to prove that you're given some arbitrary measure and you want to prove that it's more invariant than you assumed. And this is the kind of step that we're establishing here, that your measure has extra invariance under this Q and I condition. So to put it contrapositively, if you've exhausted all your invariants, so if you cannot be more invariant than, so you cannot keep growing, because the dimension of this group always grows every time you apply this theorem. So eventually you reach a point where you can no longer be invariant by more than what you have. So this means that this Q and I condition fails. So then I have to explain what this Q and I condition is. So the Q and I condition means the following. So, let me say it first in words. So as I said, you have the stable and unstable manifolds, and when you have these kinds of theorems, you can apply them both to the stable and unstable direction. And when you have only subsets of your stable and unstable manifolds, what you can do is you can start at a point and you can draw one piece of the stable manifold and one piece of the unstable, and then you have 2 points that, so let me just try this here. So if you're at a point Q, you can take a point Q prime on the stable and a point, let me call this Y, at the unstable. And now I want to say you launch again the unstable here. So, but you actually only take the U plus. And whereas here you launch the center stable manifold of this Y. And if you count the dimensions, you expect these things to, I mean, if you had everything of full dimension, then these things would intersect. But if you're of intermediate dimensions, then you would expect these things to miss each other. And they would miss each other unless this, all of these points are stuck on a submanifold. So if there's an intermediate submanifold, then these things, this quadrilateral would close up. If there's no intermediate submanifold, then it doesn't have to close up. And so this Q and I condition says that the distance, that if you zoom in here, if this is roughly of order R, and this is of order R, then this should be greater than some power of R. And this alpha can be arbitrarily large. So let me try to write it. This is what I have here. So again, the precise statement is actually quite technical because you have to
find that they the adjustment as well as integrating with a formula that is well used. And furthermore, there's a special case. You assume that this inequality is strict. So not only do we think draw something uniform that we have over here, then there's only two possibilities. We might introduce this manifold line. We have to have the volume of IQ, or we can rather more than because the integrated some part that keeps the y goes down with the momentum. So, as I said, this basically the S1 action is surprising because it's how it is.
Okay, it's back. So let me state a more elementary version that involves random walks, and it's exactly parallel to this theorem with SL2R actions. And it's the following. So you take finitely many volume-preserving diffeomorphisms of a manifold Q. And you put some weights, some probability weights on these diffeomorphisms. And so what you get is a probability measure on the set of diffeomorphisms of Q that preserve volume. And we want to make an assumption which is analogous to that subharmonicity assumption. So we're calling it uniform expansion. And the requirement is the following. There exists some uniform n with the following property. For any d between 1 and the ambient dimension, and for any orthonormal basis, we want for Vd, if you define again, the same kind of function, but now G is not an element of SL2R, but it's an arbitrary diffeomorphism of the manifold. So what do? You have your diffeomorphism of the manifold, you apply G to each tangent vector, and you see how much this tangent direction has grown. And the requirement is, again, that you have growth on average. So the average of this function f, and with respect to the measure nu, but you convolve it with itself n times, which simply means the following. To obtain obtain the diffeomorphism f, what you do is you sample randomly one of the phi's with this probability pi, and you compose things capital N times. So you make such a random walk, and you require on average vectors to grow as you apply this diffeomorphism. So you take this average. So again, this is kind of an analog of that subharmonic property. And the conclusion is that if you have such a measure mu, which is nu stationary, so what does it mean that it's stationary? It means that it doesn't have to be invariant by each of these diffeomorphisms, but if you apply the diffeomorphism to the measure, you get a new measure, and you multiply it by the probability P1, and then you do the same for all the diffeomorphisms, and you average it, then you get back your original measure mu. So this is a much weaker property than being invariant by each of these diffeomorphisms. So we assume that mu is some arbitrary stationary measure. It's ergodic, and we also assume that this uniform expansion condition holds. Then, again, we conclude that mu is in fact preserved by all of these diffeomorphisms. So initially, we only assumed it was preserved on average, but here we can conclude that it's actually preserved by all of them. And again, there's a statement to the effect that the measure looks like a volume class measure on some intermediate submanifold. And again, it's a little bit more technical to state what that means precisely. But importantly, this inequality star, if this inequality is strict, so if you can put strictly greater than 0 here, then again you have only two possibilities. Either mu has to be the original volume form, or the measure has to be finitely supported. So you can have, so to say it differently, at the topological level, what this means is that if you start with an arbitrary point on your manifold Q, you can apply arbitrary combinations of these diffeomorphisms, and either you're going to be dense on the manifold and in fact be roughly uniformly distributed, or you're going to be stuck on a finite set of points. So only two possibilities can occur once you have more than. So one thing I didn't say, and I realized that this n should be at least 2. You should have at least 2 diffeomorphisms, because if you have one, this is not true. So in fact, if you have just one diffeomorphism, this is very badly false. So such statements are definitely not true in many ways. So the initial invariance is the randomness. So you have the random walk. The Q, the manifold Q in this case, is replaced by the Bernoulli shift with times the manifold. So really, your invariance comes. Yeah, so it's a little bit like that, but yeah. So, but it's not formulated in terms of a p-adic invariance, but yeah. Okay, so I want to conclude with maybe just a few comments about these theorems. So one is that so we need this Q and I condition, and it's a little bit of a technical subject, but so I didn't say much about it. But in general, we expect that there are other equivalent ways to formulate this Q and I condition, which eventually should, at least under favorable additional assumptions, should be able to give you these intermediate submanifolds. So you should be able to obtain not just these kind of formal manifolds at almost every point, but actual submanifolds. And the other point is this assumption you need to check that is related to expansion, to having this uniform expansion. And in fact, in the Teichmüller dynamics case, this comes from Hodge theory, and we expect that, in fact, we know that this holds for interesting group actions that come from algebraic geometry. So one of these, so when you have what's called the character variety of a compact Lie group, so this is the set of representations of a fundamental group of a Riemann surface